All right, so today we're going to start with section 5.6, which is integrals of exponential and log functions. And so we've actually seen this already quite a bit. We've sort of snuck it in there under the disguise of, well, we know what these derivatives are, so what might that integral be? And so today we're going to formalize that, but particularly in the context of what happens when we have definite integrals or what happens if we have U substitution. So that kind of is going to be more the level of problem we're going to take a look at today. We've got a bunch of examples for 5.6. We've got a bunch of examples for 5.7. So hopefully it'll help us feel a little bit more rooted in learning these different rules, okay? And so we begin today a little bit differently. We're going to start just with the list of the integrals, all right? So the integrals of exponential functions, one that I think is quite familiar to us is if we take the integral of e to the x dx, we're going to end up with e to the x. Whatever function we start with that e to the x, we will end up with as our integral. And then because there's no bounds, like there's no top or bottom number, we have to make sure we put that plus c at the end, okay? Some textbooks do a capital C, others do a lowercase c. If you're handwriting things, it doesn't really matter too much. You just need to demonstrate that you know that there is a constant at the end. Now, I would say, we've gone through so many different kinds of rules. This one, my highlighter got really small. This one, I would say, is so very important to know. Okay, it is one of our sort of fundamental rules. You'll see that a lot in problems. But while we're here, I did want to include sort of a more secondary rule, a situation where maybe instead of a base of E, you have a base of A. All right. And it turns out that the one difference is you're going to divide. You're still going to get a to the x, but you're going to divide by the natural log of a. Right. And so if we think about all the rules, sometimes people are like, well, why do we have so many different rules? I mean, the exponential one, the e to the x, is actually a very special case of the second one, because if we apply that second rule, we would get e to the x over natural log of e plus c. And one of the nice numbers to know is that the natural log of e is actually 1. And so we really have e to the x over 1 plus c, or we can just say e to the x plus c. Okay, so a lot of times we sort of learn this simple case and we're like, why is the other case so complicated? But it turns out that they both follow this second rule. It's just that e, when we take the natural log of e, it's such a nice number, it goes to 1. We don't have a fraction anymore, so it seems more simple. Okay. I would say if you're going to pick one to memorize, that first one is super valuable. The second one, you see a little bit less, but you just should be aware that if that base is not E, you have to do something with it, okay? You have to accommodate for that somehow in your integral. Next, let's move on to the integrals of log functions. All right. Now, similarly, this one right here, the integral of x to the negative 1 dx is the natural log of x plus c. This one we've seen, in fact, I think I made us write a little bit something on a discussion that said, what is the one exception to the power rule? Sometimes it's sort of disguised like this, 1 over x dx. But if we have the power of x being a negative 1, that is our one exception to the power rule. And so we have to say that we don't use the power rule, but that integral is natural log. Does a refer to a particular variable or just a non-x variable? Great question. We should clarify that. So in this case, a is a constant. All right, so a is a constant. In particular, like over here in the first rule, A is E. E is a constant, it is a number. It's an irrational number, but it is a number. And so maybe a question that you might see, for example, 2, or for the second rule, might be like the integral of 2 to the x, or the integral of 3 to the x, or the integral of 10 to the x. Does that make sense? Yeah. Okay. All right. Now I threw these other rules in here just because I think it's good to see that when we're taking the integral of natural log or a regular log with some other base, we don't get 1 over x, right? We cannot just sort of switch these two. We can, if we're doing integrals and derivatives, we can sort of switch those two because integrals and derivatives are inverse functions. But the integral of natural log of x is actually this more complicated looking function. And then similarly, if that base is not e, that base is a different number, we have to compensate for that by dividing by that natural log of a. All right. Now, I would say the yellow one, that integral of 1, x to the minus 1, you definitely should know that one, okay? But I will say that these other two, all right, so these two right here, you do not see very frequently. Okay, you do not see that very frequently. I wouldn't memorize those. Truth be told, beyond the sort of foundational ones that I've been like, that show up a lot in the problems that we do, that we've done a lot of practice on. Aside from those, there are tables of integrals that you can just look up, right? And so I would say like the integral of natural log or regular log or a to the x would sort of fall in that category of look it up in a table, whereas the first two we use so frequently that it's like we should really know those, okay? So let's go ahead and get started. All right, let's work that integration part of our brains. We're going to take a look at this example right here. All right, so the integral of e to the x dx. This is not a trick question. What is this integral?
E to the x.
Exactly. So we know that this is going to be e to the x. We want to make sure that we have our plus c at the end because there are no bounds. And that's it. Okay. And so when we see a question where we have e to the x, we should be like, yes. However, what is the integral of e to the negative x? I made one super, super small change.
Is it a negative e to the negative x?
Where did that negative in the front come from? And I see Juan's got a different variation in there. Okay, so the one thing, I know these are two very simple examples. However, yesterday we learned about something called U sub or U substitution. And sort of our clue for when we needed to use U substitution is like if it's not just an X, or if we see something that doesn't totally match a rule, we might need to use U substitution. Now, I would consider example 2 a sneaky case of U substitution, all right? And so here's why it's so sneaky. It turns out that in order to integrate this, we need to set u equal to e or to negative x, meaning we're going to let u be the entire exponent up here. Okay. Now, if I find my du, I'm going to get negative 1 dx. And if I look in the question, I forget what color we used yesterday, but if we look in the question, I only see a dx. I don't see a negative 1 dx. And so our trick from yesterday is we're going to go ahead and divide by that negative 1. And now we can say everywhere we see a dx, we're going to put a negative du. all right? And so when we rewrite this, we get the integral of e to the u times negative du. Some of us might be ready to jump straight to the, I'm going to bring the negative sign to the front. All right. And now, if we look at the integral part, integral of e to the u du, that is basically the same as the integral of e to the x dx. And so now we can take our integral and we get negative e to the u plus c. The question was asked in terms of an x, so I better answer in terms of an x. So we get negative e to the negative x plus c. All right. I think it's a little bit less common that we see it written like this. All right. That's not mathematically wrong, it's just a little bit less common. But when we take that integral, we want to make sure that we're saying, all right, I recognize that I need to use u sub. I'm going to apply u sub and get a slightly different variation from my answer in example 1. Okay. So questions about example 2 right here. I think example 1 was pretty straightforward, but example 2, again, that's that subtle touch right there. We got to make sure we do u sub when we need it. Okay. All right. Well, let's continue on. We've got so many examples to take a look at today. Some of them I think are a little bit more clear what rules we need to use, and some of them are a little bit more complicated, all right? But what are our thoughts on example 3? What rule or rules might we use to take the integral of x squared e to the negative 2x cubed? Ah, all right. I really appreciate these very different answers, right? So if we were taking a derivative, we would 100% use the product rule here, right? If we were taking a derivative, we would use product rule. And when you get to Calc 2, there is a product rule for integrals, but we don't learn that in Calc 1. All right, so be on the lookout. It is one of the first things you learn in Calc 2. All right, there's something called, all right, so the integral version of product rule is called integration by parts. Okay, so be on the lookout for that. When you see integration by parts, you learn that in Calc 2. That is the equivalent of product rule. Right now, we're focusing on the equivalent of chain rule. And sometimes it's really hard to tell the difference because this looks like a product, right? X squared times something else. But I think we're going to go more with Abby's line of thought here, because one of the questions I asked us to think about yesterday is, when you look at a question, do you see a function and part of its derivative? And if we zoom in here, we might see that we have this negative 2x cubed. And we know when we take a derivative, we're going to end up with like an x squared power, all right? And so that's a really good clue for us that we're going to use u sub. And we're going to go ahead and choose the power of the exponential to be our u. All right, so yesterday we saw a few examples where like things were under square roots, and I was like, the thing under the square root is most likely your u. Well, another sort of good clue is if you have a power and like a function in a power, that function is also likely to be your u. Okay. So we've identified a u. Let's go ahead and find our du. We get negative 6x squared. Don't forget the dx. Now, how do I take this expression and match it perfectly to what I have in the question? Exactly. We can take that constant, and before we substitute it in, we're actually going to have to divide that away, right? And so if we divide this away, we'll get negative 1/6 du equals x squared dx. And now everywhere I see x squared dx, which is here and here, I can replace that with negative 1/6 du. Okay. And so when we make our substitution, I'm going to sort of do something more that you would typically see. I'm going to go ahead and pull the constant out to the front. So I got that negative 1/6. I'm replacing e to the negative 2x cubed with e to the u. And the x squared dx, that gets replaced with the du. Okay, now I know I'm writing this differently than I wrote it yesterday, and in particular, I'm skipping a step. Are there any questions about where this negative 1/6 e to the u du came from?
Yes, can you explain, please?
Yep. So in the future, I'm not going to be writing this step, but I think it's really important that we know where it came from. If we make our substitution like we did yesterday, we're going to have e to the u times negative 1/6 du. Okay. But because I know I have a constant, I just brought it out to the front right away. Does that make more sense?
Yes.
Okay.
Thank you.
You're welcome. Now, this is actually a really important piece because, one of the assignments, actually two of the assignments I asked you folks to do this week was to go out on the internet, find some resources and do some practice problems. But sometimes, even if those practice problems have solutions, they skip a lot of steps. And so part of this exercise is maybe they start here and then they do this as their next step. How do you fill in that blank in your brain? How do you connect those two in your brain? You might need to write more in between each step than the problem shows, and that's absolutely fine, right? This is all an exercise in learning how to look at different resources and make sense of the process with which they're going, okay? All right, so we know that the integral of e to the u is e to the u. So I'm going to get negative 1/6 e to the u plus c. But since my original question had x's in it, I better put those back in. And I'll get negative 1/6 e to the negative 2x cubed plus c. Right? So 3 different questions that some involve u sub, some do not, but all involving the integral of an exponential function. All right. All right, let me pause here for a moment. Are there any questions so far? All right. Well, the goal of today is just to do a bunch of questions. All right. So we're gonna or sort of keep moving. Is that called integration by parts? No, no. We are not learning integration by parts in Calc 1. Integration by parts is in Calc 2. Yeah. All right. So we are using chain rule. We are using U sub. U sub is like the one technique that you should leave Calc 1 feeling really solid about for integration. All right. And it's always a really good technique to use. You're going to see a lot of really complicated integrals in Calc 2, like way crazier than what we're taking a look at here. You're going to learn a lot more techniques, but it's always worth trying U sub first, because sometimes we overthink things and we're like, oh, it just has to be like, you know, something more complicated. But a lot of times we can bring it back to those fundamentals. All right, so I see a question in here, straight solving, yes. I wish I could tell you chapter 6 is going to be like this. It is not. Chapter 6 is so visual we actually take things from 2-dimension into 3-dimension. And I can't think of a better way to finish off the summer. So no, the short answer is no, chapter 6 is not like this. But today you will get a little bit of reprieve. All right, so let's move along. Let's keep working on some solving of things, right? No theory, but we do have to work on our decision making. All right, so example 4. What are our thoughts here? We've got e to the x times 3 e to the x minus 2, that quantity squared. What rule or rules might we want to use here? And I'll give you a hint, we really only know one rule. So if we can't integrate it right away, we're probably going to use u sub, okay? All right, so we are using u sub. Again, that is the theme of today. That is the purpose of today, because even though we saw it yesterday, it comes up everywhere, like everywhere, everywhere, everywhere. And so I just want us to really have that on our radar, okay? What are our guesses for you, for example 4? Right, because that right there is the key to how well do we understand u sub. Ooh, all right, so 3 e to the x minus 2. And I'm so glad we just grabbed that minus 2 and kept it in there also, right? Because constants go away when we take that into our derivative. And so it is usually best to clump it in there with your u. All right, so du is going to equal 3 e to the x dx. I take a look at what I have in the original problem. I see the dx and I only see an e to the x. So I'm going to go ahead and divide both sides by 3 before I substitute. And now everywhere I see e to the x dx, I can replace that with du over 3. Okay. Now, as promised, I'm not going to write the second step. I'm going to jump right to the next step, where I bring my constant out to the front. What is the constant I should have in front of the integral I'm about to write? Exactly. I'm going to take that 1/3. I'm going to bring it out to the front. I'm going to have the integral of u squared du. Okay. Now, me skipping a step does not mean that if you don't skip the step, that you write it out for yourself that like, oh, I don't think you're good at this. Okay, I just want to be really clear about that. Part of this is very intentional, knowing that, especially when you start to get to Calc 2 and Calc 3, not every professor shows every step, and especially in Calc 2, because like some of the problems are so long, they just don't show every step. And so learning how to connect those dots is actually a really important part to your mathematical practice. Okay. But check this out. We did this u sub. Turns out all we need is power rule. Well, that's a very nice way to start off the morning, right? So we're going to have 1/3 u to the 3rd plus c. And so my coefficients become 1/9. But everywhere I see a u, I'm going to put 30e to the x minus 2 cubed plus c. All right. Any questions on example 4? Ah, that second 1/3 came from the power rule of u squared, right? So the integral power rule is you're going to take that power, you're going to add 1, and then you're going to divide by that power plus 1. Yep. Right, so our power rule reminder, the integral of x to the n dx is x to the n plus 1 over n plus 1. Okay. All right, let's move along. More straight solving. It did. And I think that this is another sort of piece to it. Some people write it as a single fraction like this, right? And some people prefer to bring the constant out to the front and keep the rest of the power part off to the side, right? So I would say those are the two different ways that people will write things. All right, let's take a look at example 5. This looks more complicated than a regular looking integral. So my guess is we're gonna have to use the one technique we know. But as you move into Calc 2, you do want to think, which one of my techniques might I want to use, right? So if whoever your Calc 2 instructor is, you should ask, well, how do I know I'm going to use this technique? How do I know I'm not going to use this other technique, right? Those are good questions to ask. Those are good things to know about how you're going to apply things, right? I trust you all to do the procedure, but do you know when you're going to use it? That's something that you often have to advocate for yourself. Okay. But knowing that we have u sub here, a good guess for our u exactly is the entire term underneath that square root. And so we find our du and we get e to the x dx. Check that out. That constant just went away. So everywhere I see e to the x dx, I can replace it with du. And so we do our integration of u to the 1/2 du. So that's a good place to say, I skipped a step, right? I didn't write it as the square root of u. I said, I know it's going to be the square root of u, but I know I'm taking an integral, so I want to see that power, u to the 1/2. Now, one thing that's interesting is a lot of answer keys or websites might not actually write this part. They might just keep it as the square root of x or square root of u, and then just have magically the integral there. But I would encourage you to write this step, right? Prove to yourself that you know what that power is, and that even though it's a square root, it's just the power rule with some fractions, and that's okay. All right, so our power rule, we're gonna have u to the 1/2 plus 1 over 1/2 plus 1. That's how we typically write it, right? Plus c. And we're gonna get u to the 3/2 over 3/2 plus c. My guess is no answer key will show you these steps, but we want to make sure that we know where their answer came from, right? And if we have to write the extra steps in there to make sure we know where that came from, far be it for us to skip that, right? And yes, we do want to flip that denominator. So we're going to get a coefficient of 2/3 u to the 3/2. So 2/3 1 plus e to the x to the 3/2 plus c. All right. Now, I know I'm skipping some more steps and we're sort of moving through these questions a little bit more quickly today. And I'm not doing that to sort of intimidate you, right? Or to say like, oh, you should be at this point, because I think we all learn in different ways. And if we want to write extra steps to make sure we understand, you should 100% do that, okay? It does not make you a worse math student. It just means that I, on the instructor end, am being a little lazy right now. All right. Then trying to also like put forth this idea of how do we connect those dots, right? So I've been in my own math classes and I've had professors skip steps, and I will go back and I will annotate all of the missing steps in there, because if I don't do that, then it's hard for me to understand where my answers came from. I think I always felt a little judged doing that. And so that's why I really want to bring it out there that like, if you benefit from doing that, then do it, right? I think life is too short, semesters are too short to say, oh, I don't want someone else to see that I wrote more things. All right. Well, let's go ahead and take a look at one more indefinite integral. All right. Now, how do I know from looking at this that I'm going to need u sub? I have e to a function, good. And let's be more specific than that, because you could have a case in Calc 2 where something looks very similar to this, but you can't use u sub. It is a product, but again, that product is going to be more a symbol of I should use that integration by parts technique. There's something very subtle about what the functions are that tell us we should use u sub. Not quite, not quite. It all goes back to the question that I asked yesterday, which is, do you see a function and part of its derivative in the integral? Okay, so in particular, we're looking for a function and part of its derivative. Okay, this more than anything is the most important clue to say u sub. All right, let's do the u sub here. All right, we see something in a power, Jeremy's right. And if we take that derivative, we end up with 4x cubed dx. That is super similar to what we have in the problem, but we're looking to match 2x cubed dx. And so all we're going to do is divide both sides by 2 so that we can match perfectly. 2x cubed, we're going to replace with du over 2. So if we bring our constant out to the front and we substitute, we end up with something like this, which is going to be 1/2 e to the u plus c, which is going to be 1/2 e to the x to the 4th plus c. All right. The thing in the pink, that when you look at a function and you see a function and part of its derivative, that is the clue for u sub. Okay. I'm going to write something in red right now. I'm going to write it in red because in this case, we would not be able to use u sub. If I changed the question to I changed one number. In particular, it's not 2x cubed anymore. It's 2x to the 4th. Exactly. Okay. If I saw this problem, I would try u sub first, maybe just mentally. You don't have to write it out, but I would think, I see an integral, I'm going to try u sub. That's my go-to, my bread and butter. But if I set my u equal to x to the 4th, my du is going to be one smaller power. That's not going to get rid of this 2x to the 4th. Okay, so this right here in the red, we would use integration by parts. Okay, so this is an example of, like, in Calc 1, we learn this one technique, we use it all the time, and you get to Calc 2, and nobody tells you that suddenly you're going to be learning a bunch of other techniques. So then it becomes very foggy, like, when do you use which one? Okay, so in this case, the reason why you would use a integration by parts is because of the product and because you do not see a function and part of its derivative. All right, I don't want to get too far into that. I do wish that we taught more than one technique for integrals in Calc 1, because I think that decision making is hard to know unless you have something to compare it to. But you can sort of consider this, that you're really looking for a function and at least part of its derivative. And if you have that, you should be on your merry way with u sub. Okay. All right. Let's do some definite integrals. Get that practice in there. See what it looks like to simplify things with e, because there are some quote unquote nice numbers that are valuable to know. Okay. All right, so let's take a look at example 7. All right, I see a function, e to some function, and I'm thinking it's not just e to the x, so maybe it would be valuable to do u sub, right? Now in this case, it's a sneaky case because I don't see the derivative necessarily, because the derivative is just a number. And that constant, we can manipulate, or we can divide it away in order to match the equation, right? So this is that sneaky case. Now, as we talked about yesterday, there's sort of two camps of thought on how we set up our integral. I like to, once I've gone into U land, I like to stay in U land, right? So here's my integral, but I'm going to go ahead and change the 1 and the 2, because these are x numbers, so that I can have u numbers in the other part. So to find the u numbers, u of 1 equals 1 minus 1, which is 0. That means the bottom number is 0. U of 2 is 1 minus 2, which is negative 1. Means the top number is now negative 1. Okay. Now this next part is optional. I think it is a handy trick to sort of wrap your mind around them. So in one of the videos I had you watch last week about properties of integrals, there was something about like the bounds of the question and like switching the bounds. Does anyone remember what that property is? Like if I switch the bounds, how does that change the value of the integral? Okay. So in particular, it changes the sign. So if it was positive, now it's going to be negative. But if it was negative, now it's going to be positive. Okay. And so if we use that idea here, I'm going to have a negative, I'm going to have a negative, negative, negative 1 to 0, e to the u du. The nice thing about using this property is the minus minus becomes a plus, and we have negative 1 to 0 of e to the u du. Right, so it's a little bit nicer to work with because I don't have a negative, and traditionally we like that bottom bound to be a smaller number and the top bound to be a larger number. Okay. Once we do that, we can go ahead and plug in our bounds, e to the 0 minus e to the negative 1. This is a special number here. What is e to the 0? Good, so this whole thing I can replace with 1. So I get 1 minus e to the negative 1. I could also write this as 1 minus 1 over e. Okay, but it is fine to leave it right here. All right. Any questions on example 7? All right. I'm going to leave example 8 as one that you can come back to if you want to practice some U-sub. I will tell you what the answer is. And so part of this will be, can you match this particular answer? So 1 over 2 e to the 4th minus 1/2 is the answer you're going to look for example 8. Okay. Okay, so I got a question in the chat about why we didn't bring it back into X land. Because if I have bounds, I'm looking for a number. So I can go from X land to U land and back to X land, or I can just change everything to be in U land, and then I don't need to change it back anymore. So as long as you change everything about the problem, like the U, the bounds, if everything is in U, then you don't need to change anything back. And yes, that's only with definite integrals. It's only with definite integrals. Great questions. Cool. All right, so example 8, I think, is well within your wheelhouse to try and solve. But I think something like number 9 is a little bit more of one of those, like, it's a little bit of a twist to a problem. And so we really want to make sure we know how to handle those, okay? And so one of the things that makes this complicated looking is there's sort of like lots of fractions and exponents going on. And so I might take a moment to write this out a little bit bigger. So I have the integral from 1 to 2 of e to the power of 1 over x over x squared. Okay. Now, I don't know that you would know to do this, but I'm going to write this function in a different way so that it might be a little easier for us to see how come we can use U-sub here. And in particular, I might write this. Okay, so go with me for a moment here. I know that this next step, I would never expect you to do this next step, but to help us see where this idea of U-sub comes into play here, I think it might be beneficial. So a good guess for you might be the thing in the power, right? So e to some power, that power happens to be 1 over x. But I know I'm taking a derivative, so maybe it's helpful for me to write it with the power visible. So when I find my du, I get negative x to the negative 2 dx. All right. So maybe from here, it's a little bit more clear. I have x to the negative 2 dx. I have almost x to the negative 2 dx. Exactly. I can divide that negative away. It's going to allow me to perfectly match that last part of the function. Okay. Now, this is actually a good follow-up to the question I just got a little bit ago. I could put this back all into X land, but I could also just change my bounds, make the 1 and 2, which are X values, into U values, and then I don't need to go back. And so I'm going to go ahead and do that. So U of 1 is 1 over 1, which is 1. U of 2 is 1 over 2. So I have a bottom bound of 1 and a top bound of 1/2. Okay. Now notice that that top bound, 1/2, is actually smaller than 1. That tends to make mathematicians uncomfortable. And so this might be a good place to also take my top and bottom bounds and switch them. And that would change this negative sign in the front to a positive sign. Okay. Optional, but happens a lot in a lot of answer keys. All right, so it would be worth at least understanding where that step comes from, even if you choose not to use it. All right, we plug in our bounds, e to the 1 minus e to the 1/2. E to the 1, I can just write as e to the 1/2. Maybe I write that as a square root of e. But we would want to leave things in terms of e. We would not want to type this into a calculator and get some decimals. Yes, one, if I didn't do that and I left a minus sign there, I would just have a lot more minus signs in my answer. But then all the minus signs would cancel to make a positive e and a negative square root of e. Right, so you just got to be really careful. And I know that at least for me, like when I have more negative signs in my question, I tend to make more mistakes. And so if I can get rid of some of those negative signs, I'm less likely to make those mistakes. So I think that's why we tend to do that. Okay. All right. Now let's say in this question that you were like, I would never think to write it like this, x to the negative 2. Well, if you left the question like this, it might be useful to write your du as negative x to the negative 2 dx or negative 1 over x squared dx. Okay, so all summer long, we've been working on positive and negative exponents. How do we go back and forth between the two of those? And this is just another reason why it's so important to know how to go back and forth between these two versions, because sometimes it's written a different way in the problem. And if you don't know how to go back and forth smoothly, you might miss out on how to solve that particular problem. Okay. All right. Example 10 is actually similar in flavor to example 9. And so same thing, I'm going to leave this as an answer for you. E to the 4th minus e over 8. All right. And so if you are looking for problems to practice for U-sub and you have not found a good resource, this could be another one to come back to and try. Okay. All right. So we've got about 5 more examples, I think. And we're going to kind of pick and choose and see where we're at and what feels like something that we could sort of model on our own. Absolutely, absolutely. So you might notice that I'm not doing all of these problems, right? And so someone has asked, could we use these questions as part of the 10 practice problems? 100% you can, okay? Sometimes it's hard to find a good problem. All right, so let's choose either 11 or 12. All right, so 11 or 12 are sort of similar in flavor. Which one of those would we like to see? All right, I see a vote for 12. All right, let's go ahead and do 12. And since we're going to skip 11, let me give you the answer for 11. Okay. And let's do number 12. All right, what are our thoughts? I think we see a sneaky U sub here. What might be a good thing to put in for you? Good. I see a few guesses that let's just take the whole denominator and let's set that equal to our U. Well, let's see what happens, right? Because I said yesterday, sometimes you write down a U, you're not really sure, but when you find your du, that actually tells you. So if I find my derivative, I get 3 dx. Now I am trying to make 5 dx, but we don't have to worry too much about that. And I'll tell you why. Let's just go ahead and divide both sides by 3. And now let's make our substitution, okay? So in other words, I am matching just the dx with the du over 3. The reason I can do that is because this 5, I can actually bring out to the front like a constant, okay? So I'm gonna have 5 thirds because the 5 from the 5 in the numerator, the thirds from the 3 in the denominator. Together give me a constant of 5 over 3. 5 over 3, the integral of 1 over u du. Right? And if you're not quite sure how that happened, I would encourage you to go back after class, write out a few steps in between. You can send that to me on Discord and say, like, is this how you got to that point? Okay. All right. Now, the benefit of this particular integral, it is one of our rules, right? This is our exception to the power rule. And so we can say 5 thirds natural log of the absolute value of u plus c. But at the end of the day, everywhere we see the u, we're going to put back in our 3x plus 2 plus c, and we'll call it a day. Okay. Let me ask you a question. What if I had this? Does u sub work here? Good, good. Why? Yeah, we can't use u sub because if we say u equals 3x squared plus 2, we're going to still have an x in my du, and there are no extra x's here. Okay, so in particular, we could say u equals 3x squared plus 2, du would be 6x dx. I could deal with the 6, but there's nothing I can do to handle that x. All right, and so this would be a good example of not u sub. Okay, not u sub in this case. So we really want to pay attention to those small details. A number can be changed, a power can be changed, and all of a sudden that technique doesn't work anymore. All right. All right. So I know I heard 13 and 14, or 14 and 15 as choices. Do we feel okay about example 13? I think this one could be one that you work out on your own. I don't want to presume too much though. Would people like to go over this one? Okay, cool. All right, so we've had a few people say yes, 13 would be worth looking into. All right, so I would say based on the powers that I see, like a fourth power and a second power, and then I see a third power and a first power, I might notice that like if I lose a power from 4, I get 3. If I lose a power from 2, I get 1. And so that might be a clue that we're going to use up. And we want to choose the one with the higher power. The higher power so that when we take a derivative, we actually end up with the other piece. That's the goal. So du would be 4x squared plus 6x, or 4x cubed, excuse me, plus 6x dx. How do I make what I have here, whoops, how do I make what I have here match what I need it to match in the exact or actual problem? Yes, look at that, folks. So we can divide, right? We've seen that we can multiply sometimes, and sometimes we divide. And that idea of knowing like what is a factor that goes into all of the terms is really handy here. 2x cubed plus 3x dx. Wonderful. Everywhere I see this, I can replace it with du over 2. And so we get 1/2 the integral of 1 over u du. Wow, that use of really cleaned things up, right? Look at how messy it was before, and with our identification of the correct u and a little bit of algebraic manipulation, we were able to turn this into a 1/2 integral of 1 over u du. So 1/2 natural log of u plus c. Now, different instructors will be picky about the absolute value in different ways. And in particular, I'm speaking about that Calc 2 professor, okay? You tend to see those natural logs a lot more in Calc 2. It would be a very, I think, helpful to your success to clarify with your instructor about how much they do or don't care about the absolute value, okay? If you're not sure, I would always include them. So like something like this would be like, okay, you're following the rule, all right? But let's say you looked up this question on like a website and it showed you how to do everything. And at the end, they had this. And I would argue that this is a more correct answer. Even though I just said that the absolute values are really important. Why would that be a more correct answer? What are our ideas around that? Brilliant, brilliant. Okay, so if I take the piece that is being absolute valued, x to the 4th plus 3x squared, x to the 4th is always going to be positive. 3x squared is always going to be positive. And when I add a positive to a positive, it's always going to be positive. And so it's always going to be positive. I can drop the absolute value and say, Oh, just parentheses, just that expression. Okay, and you'll see this in like the upper level math classes where you might even have a professor who's like, oh yeah, you better have those absolute value signs there. And then all of a sudden they don't write it. And you're like, what are you doing? You just told us that we needed to write the absolute value sign. Sometimes it's as small as, can that thing inside your absolute value even be negative? Because if it can't be negative, then we don't need to use the absolute value sign. Okay. Also, I feel like if you ask that question, like, oh, did we lose the absolute value because everything in there is already positive? I mean, it makes you look like you could really connect the dots in your math class, right? So think about that. All right. So I saw a lot of people wanted to do 14. I'm actually going to say we do 15. All right. I will give you an answer for 14 in case you choose to use this one as one of your practice ones. All right. So it turns out that at the end of the day, you should end up with natural log of 2. All right, so I'll just let you sit with that for a moment where you're like, I was in trig land and all of a sudden now I have natural logs going on. Like that's kind of a lot for your brain to handle on a Wednesday morning, right? But I promise you that if you set up your substitutions correctly and you use the proper trig values, that you'll actually end up with natural log of 2. All right. Now, I did want to do 15 because 15 is one that is both a question and a derivation of something, meaning you can look up a formula for tangent, like the integral of tangent, okay? You can look that up, not a problem. In fact, if you could look that up right now, let's maybe type into the chat, what is the integral of tangent? That's not one of the rules we know. That would be one that you likely find on a table or something like that. All right, so let's flex those Google muscles and let's figure out what the interweb says about the integral of tangent, not of from 0 to pi over 4, but just the integral of tangent. The derivative of tangent is secant squared, but I want to know about the integral. Yeah. All right, I buy that. I think that is one option. Someone find a different answer. Right, and in fact, I'm going to go ahead and take the bounds out of this question based off of what we're finding here. So I agree that one possible answer is negative natural log of cosine of x plus c. I agree. But there's another version of this answer. There it is. Natural log of secant of x plus c. Now, how could an integral be two different things? Well, turns out these are one and the same, okay? So once upon a time, I was taking a math test along my journey to become a math teacher. And this was a question on a closed book test. And I was like, I don't know. I always tell my students to look this up on the table. I can't believe they asked me to do this. And then I realized that a little bit of trig goes a long way. All right. So in particular, what is another way that I can write tangent? Yeah. Another way to write tangent is sine over cosine. And this is really where the story begins, okay? So sine over cosine is another way of writing tangent. Well, I don't know what that integral is. And the only technique I know so far, if I don't know what it is u sub. So let's try u sub. What would be a good choice for the u in this case? Oh, you already beat me to it. Cosine x. Okay. We've said some clues about what's a good u. Underneath a square root, in a power, but also the denominator is a good choice for the u sometimes as well. Okay. If I find my du, I get negative sine x dx. I see a sine x dx, but not a negative, so let me bump that -1 to the other side. Let me make my substitutions. Negative the integral of 1 over u du. Negative natural log of the absolute value of u plus c. Everywhere I see a u, I'm going to replace it with cosine x. This formula, negative natural log of cosine of x plus c, well, they get that answer using u sub. All right. So if you've ever been like, how do people find what these rules are? A lot of times they're just using some of the other rules we know and working it out. But because we see it so frequently, they're like, oh, it's just negative natural log cosine of x plus c. Okay. Thank goodness I remembered my trig that tangent is sine over cosine, because I did get that question right on the exam. And that was actually the purpose of that question, was to say, even if you don't know something, how can you figure out that something based off of what you know? Right? Now, let's think about how we get the other version of this answer, right? Because both of them are true. Now, both of them are true, which means that in some contexts, the first version is going to be more useful. And in some contexts, the second one is going to be more useful, all right? And depending on how far you go in math, you will find situations where it'll be clear where one is more important than the other. But I think in a case like Calc 2 or something like that, more immediate in your future, it's a little bit less important to know which one is more useful, okay? But I do want you to know they're the same. And so we're going to use some log properties now to prove to ourselves that these are the same. And in particular, there's a property of logs that says that the coefficient can be bumped up as an exponent. And so we have natural log of cosine x to a -1 power. All right. Now, I think one of the reasons trig is so tricky is because we use the same symbol for things, but they don't always mean the same thing. And this -1 here does not mean the inverse. Rather, this -1 means reciprocal. And so we could say this is natural log of 1 over cosine x. And the reciprocal of cosine, that -1 is from that coefficient. So there's a log property where you take that, you can take the coefficient and you can bump it back up to the power. Like a like 2 natural log of 5, if you type that into your calculator and then you separately type in natural log of 5 squared, like natural log of 25, they're gonna be the same number. Okay, so that power you can bump up at, or the coefficient you can bump up as a power, all right? And so we are one step away from seeing where that other rule came from, because 1 over cosine is secant. Ah. So this second version is just using some algebra to manipulate the first version. And the first version came from u sub, right? So an interesting exercise in thinking about like where all these different rules come from, why there's more than one version. But I think that this is sort of an important derivation to see at some point, because I mean, are we going to use u sub in our real life? I mean, probably not. Like, I mean, in your real, like, non-academic life. However, you're sort of stepping into the shoes of mathematicians here, right? I mean, you are mathematicians. Whether you feel like you're good at it or not is a different issue, but you are mathematicians. And so using things that you know, lots of different pieces, right? One piece from trig, one piece from calculus, you're able to actually come up with the formula. And I think that's something to really celebrate, okay? All right, so it is 8:16. I'm gonna stop recording right now.